let's look at how the binomial model relates to the normal model with a few quick demos. Here's the setup. We've got a binomial model situation. Something that's modeled accurately by a binomial model. For example, we're going to discover that sampling from a population is modeled exactly by that, or at least as exactly as we can expect. And we've got this binomial situation, so we've got n Bernoulli trials, and each with a probability of success p, probability of failure q equals 1 minus p. So we do have a formula for this. It's the probability of having x successes is n choose x times p to the x, q to the n minus x. Problem is, it turns out that especially this coefficient, and then definitely these guys, these could be very high powers if n and x are big numbers. This could be fairly unwieldy even for a calculator. The great thing is that exactly when this becomes unwieldy, or almost exactly when this becomes unwieldy because the numbers are getting so big, it turns out that the binomial model tends to turn into a normal curve. Beautiful, beautiful theorem that we're not going to prove definitely, but it's a wonderful fact. Okay, and it's so what normal curve does it turn into? We just need to say what's the mean, mu, and the standard deviation, sigma, of our normal curve. And it turns out there's standard formulas for that. I'm not going to derive those formulas or talk about those right now. I just want to illustrate, using Fathom here, how that process happens. Okay, so here's a let's see if I can double-click on this. It's giving me some problems. Okay, well, this is, let me just put some new cases in here. This is a binomial variable. So let's just do the first case. It's the binomial with, let's say, I put in 12 and 1/3. So 12 tries total and 1/3 probability of success. Okay, and I'm going to strap this over here. Okay, so here's a dot plot of out of 50 trials what we're getting, and it looks like on average something like 4. Okay, yeah, that would be the expectation value. That if I have 12 trials and 1/3 of them typically come up successes, then I should get on average 4 successes. Okay, it looks like some sort of histogram centered at 4. Doesn't look particularly normal, but then again, we wouldn't expect it to look like a perfect bell curve even if it were following a normal distribution, because there's not enough data yet. Okay, so let's go ahead and put in a bunch of new cases. Let's put in like 1,000 cases. Okay, so now we're getting a distribution with many more things, but it's really still not looking like a normal curve. In particular, it can't possibly be that accurately modeled by a normal, because it's got a tail that's going up to 8, 9, 10. That's 4 units above the mean, which would be 4, and it can't go below 0. Okay, so what the book points out in their math box is that one simple way to figure out that you can't be normal, they don't say it exactly this way, but one simple way to figure out you can't possibly be normal is if the tails, if symmetrical tails would actually go off towards the negative, because you can never have a negative number of successes, okay? And you can never have more than the total number of trials worth of successes either, but here it's because the negative. Okay, let's try one more with this, and maybe try at 5,000. It's the maximum number of new cases we can add. Okay, so after this, it doesn't look any different from this after adding more. This is probably a pretty good estimate for what the real distribution is for this model, and it's definitely not a nice normal distribution. It's not exactly this curve, and in particular it's missing this tail. Okay, so let's go to another one, demo 2 here. Open that up. Okay, so now let's put some cases in here. Let's just do 10 cases to start with. Okay, so this one, the second case, this is the binomial model with, this was with 30 and 1/3. Okay, so now notice this is where NP is exactly equal to 10. 30 times 1/3 is equal to 10. And in the book, they talk about how the rule of thumb is that the expected number of successes, which is the total number of trials times the probability of success, should be bigger than or equal to 10, and the total number of failures should also be bigger than or equal to 10. Okay, in this case, that's satisfied. So this should look pretty good, although it shouldn't be absolutely amazing in its fidelity to a normal curve. Okay, so let's go ahead and do this. Okay, Alrighty, so certainly not much to start with because we haven't accumulated much data. So let's put in a bunch of new cases. Okay, this is looking a little bit more like this normal curve. Of course, it's never going to be perfect because this is a nice continuous curve and this is a discrete distribution. You're never going to have exactly 8.5 successes. So when we say that this gets closer and closer and closer to a normal, we have to be a little bit careful of that, even in the cases where the NP and NQ are bigger than or equal to 10. And I might record another video about the subtleties of discrete versus continuous. They talk about it a little bit in the book, but not a lot. One of the things to notice, though, is that our expected number of successes is 10, and it seems to be right in the middle of this distribution. And now the tails do look much more symmetrical. Okay, and let's just go and add 5,000 more cases. It chugs for a minute. Okay, that looks pretty good. And so you can see the tails are coming up a little bit. Let me move it over in case we need it. That's pretty good. But it looks much more symmetrical, and it's looking plausibly like this normal distribution. Not a proof, and the proof is actually pretty substantial to do this, but it's very cool. All right, so let's look at one more example. I don't know why it's doing that. Okay. So here's one. Let's see, I've already added 50 cases to this guy. Okay, with 50 cases, you can't really tell what's going on. The third case here is binomial with, and you know, I think I'm forgetting, and it's not going to let me look at this. Let me see if I can inspect. Ah, there we go. I don't know why I wasn't able to inspect this before. Okay, now it's 100 and a third. Okay. Just wasn't letting me doing that with a double click. So let's add a bunch of cases here. Okay, so this is 100 possible total trials and 1/3 probability. Okay, so here NP is 33.3 basically, and NQ is about 66.7. Okay, so definitely well more than 10. Now again, if I do this many trials, you can see some kind of raggedness here. It's not exactly following a normal curve, but that's probably just because we haven't had an immense number of cases. Let's go ahead and put them in here. Now it's looking pretty good. We can see that the mean of this is right around 33 1/3, and it's looking pretty plausibly like this kind of bell curve shape with nice symmetrical tails. It really is pretty close to the bell curve. Again, it's a stair-step version of it because it can only take integer values, but it's definitely starting to look like this guy. So that's an illustration of how we have to be very, very careful and cannot use the normal approximation, for example, in here, where the NP, you notice, would be 4 and the NQ would be 8. Definitely not good. We could use it pretty well here, and then it becomes a very good approximation to the right distribution in cases where NP and NQ are well bigger than 10.